Alrighty, elementary educators, in this screencast, we talk about the greatest common factor of two numbers. This is something we do in the late elementary grades, maybe even early middle school. The GCF is one of the things we talk about when we go into number theory. The greatest common factor is in fact a factor of both of the numbers. It's a divisor of both of the numbers. It's a number they have in common. It's a divisor they have in common. And it is in fact the greatest of all common factors. I will illustrate three ways we happen to find those. You can use any of them at any time. Let's find the greatest common factor of 28 and 42. One of the methods that we use to find the greatest common factor of 28 and 42 is called the intersection of sets. In the intersection of sets, we write out all the divisors of 28. We write them all out. We write out all the divisors of 42. We write them all out. And then we look for common factors and we choose the greatest one. That's how this process will work. Well, what are numbers that divide 28? Well, 1 divides 28, divides it 28 times. And 2 divides 28, divides 28 14 times. 3 doesn't, 4 does. 4 divides it 7 times, and all we have to check are 5 and 6. Neither of them divide 28. This is the complete list of divisors of 28. Similarly, the set of divisors for 42 is a little bit bigger. It's a little bit bigger. But these are all of the divisors of 42. So where are the common divisors? Well, 1's a common divisor, 2's a common divisor, 7's a common divisor, 14's a common divisor. What's the greatest common divisor? The greatest common factor of 28 and 42 is 14. The intersection of sets method requires you to write out all of the factors of both of the numbers and then look for common factors, choose the greatest one. There are other ways. Let's find the greatest common factor of 45 and 75. This time, let's highlight the prime factorization method. The prime factorization method is so called because we find the prime factorizations of those two numbers. Why? Because the prime factorization breaks the thing down into the Lego blocks that make up the number. And we find out that 45 is made out of 2 3s and a 5. 75 is made out of a 3 and 2 5s. So when we go to figure out what the greatest common factor is, well, it's going to have to be a common factor, and we want it to be the greatest possible one. So common factor would have to have a 3 in it, would have to have a 5 in it, right? Like that's just sort of how we imagine this going. There are factors of 3 here, there are factors of 3 here, so there will be factors of 3 in our greatest common factor. There are factors of 5 in both numbers, so there will be factors of 5 in the greatest common factor. So what's the power that we use? Do we use this 2 or this 1? Do we use this 2 or this 1? Well, 75 doesn't have 2 factors of 3, it only has 1. And so we use 1. 45 doesn't have 2 factors of 5, it only has 1. So we use 1. Why does that make sense? Well, we want the factor to be a common factor. So we want to make sure that 45 has that many factors of 3, 75 has that many factors of 3. And so we choose the smaller of these two powers, and then we choose the smaller of those two powers. Okay, so the greatest common factor is 15. And you can confirm that doing the intersection of sets method. Well, let's find the greatest common factor of 19,789 and 20,867. Nobody wants to write out all the divisors. Nobody wants to try to find the prime factorizations. Let's do something different. Let's do something called the Euclidean algorithm. And the Euclidean algorithm is predicated upon the notion that the GCF of any two numbers is the same as the GCF of their difference. So clearly we're looking at common factors. So if you take common factors of those two numbers and then you subtract those two numbers, it's still a common factor of their difference. So the greatest common factor of 19,789 and 20,867 is the same as the greatest common factor of 19,789 and their difference, which happens to be 1,078. And then we can play this game again. We can say, wait a minute, the greatest common factor of these two numbers is the greatest common factor of their difference. And we can take out as many 1078s as we want from 19,789 until we have a very small positive number that results. And in fact, if you do that, if you take out 18 factors of 1007, sorry, if you take out 18 1078s from 19,789, because you can take 18 1078s away from 19,789, you get a difference of 385. So the greatest common factor of these two numbers has to be the greatest common factor of these two numbers. Then you can play the game again. The greatest common factor of these two numbers is the greatest common factor of of either of those two numbers and their difference. So we can take out two factors of 385. We can take out two 385s from this number and we get an even smaller number. And then we can just keep doing this. We can subtract 308 from 385. And then we notice that 308 is 4 times 77. And so the greatest common factor of 4 times 77 and 1 times 77 is 77. It will always happen when you keep subtracting, keep subtracting, keep subtracting. It will always happen that eventually one of the numbers is a multiple of the other, and when that happens, we can finish quickly. So then we can do the Euclidean algorithm and not have to worry about prime factorizations, not have to worry about writing out sets of divisors, and that is clearly preferable. Oh, let's not go there yet. That's another screencast. So you may want to consider find the GCF of 906.75 and of 14,595 and 10,856. You may want to do that. You can pause the video. I'm going to show the answers really quickly here. See, there they are. I hope that's helpful to you. We'll see you soon.